These are fractions. 0, 1, 2, 3, 4. And then we're going to try to match to everything that's a over b, where a and b are positive integers.
So all the positive rational numbers.
Yeah, that's right, positive rational numbers. Did he talk about how to do that?
I think he did.
Okay.
Yeah, I think he sort of represented it by a painting of a shark.
He represented it by a painting of a shark.
Yeah.
Okay, I wasn't expecting to hear that as the way he did it.
Yeah, I can find it in the book.
All right, go ahead. Find it in the book. This was represented as a painting of a shark. Okay.
So, here. Consider an infinite rational shark.
An infinite rational shark.
There's one tooth for each rational number.
All right.
The tip of each tooth hits the bottom lip at the corresponding point on the number line. And it seems like the shark has way more than Alphanot teeth.
Yeah.
Teeth are everywhere, but here's a proof that the set has rational numbers that's the same size as Alphanot.
Okay.
And then this is what he did. So he created this spiral sort of pattern going out.
Ah, and this has positive and negative numbers in it. Okay, well let's see if we can recreate this just for positive numbers.
Okay.
So when he had all the positive, or when he had positive and negative numbers, I guess he probably didn't allow 0 on the bottom, or maybe he even did. Maybe he said, you know, this can be, these are, instead of being actual rational numbers, maybe they're just
Integer over integer.
pairs of integers. And we're not going to worry about the dividing. But I'm going to just take positive numbers so that we always get a fraction. But we'll see that we'll have 3 over 3 and 10 over 10 and you know, 100 over 100. So we're going to be counting what we would consider to be the same number more than once even.
Yeah.
So in fact we're overcounting the rational numbers.
I think I sort of remember how to do this.
Okay.
So you look at the fractions as points on a grid.
Okay, let me draw a grid here.
So just have all these points.
And then I guess the x, you can have the x value be your numerator, and the y value be your denominator.
Okay, so this would be, we're going to say the x goes first, so this point would be 2/3, and this point would be 3/2. Okay.
And then along here would be the integers.
Okay, great.
So then, to match them up, you sort of use this snake-like pattern. So you get, I think it goes like this. You go that way, out like that.
And then you can just snake all of them.
Right.
So that's how you hit all of them.
Actually, I think here you would have wanted to go up.
Up first.
And then down, and then
So-
here you would have gone down to here, but yeah.
And then this will hit all of the numbers on this grid.
Okay, and how does this tell me that the numbers in this grid, so in fact overcounting the rational numbers, match up with the positive integers?
You can take this line,
Then you
and then the integers are going to go along here, along this line here.
Okay,
You can take this line, sort of straighten it out, and then just lay it along there.
okay.
Yeah.
What were you going to say?
Well, that was pretty much. I was just gonna I was just gonna match up points, but yeah.
Okay, how would you match up points?
Well, you could just number the points on the line. You could just go along the line and then number all the points.
Sure. Okay, very good.
And so on.
Yeah. So every time you hit a grid point, you just count up by 1.
Yep.
1, 2, 4. So this is very surprising that the fractions, and see, we said this even overcounts the fractions because
Yeah.
this counts the fractions. In fact, it counts all the fractions more than once.
And it counts 1 infinitely many times.
I think it counts all the fractions infinitely many times.
So the rational numbers would be less
Right.
than if not.
Ooh, interesting question. Are the rational numbers smaller than the integers?
Well, it would seem so because this bijection here, you've got, like you said, that you've got overcounting.
Uh-huh.
So you'd have to subtract some away so it would be smaller.
But if you subtract any finite number of numbers away,
Uh-huh.
it's still infinity.
Yeah?
But you're subtracting infinitely many numbers
Oh,
away.
puzzling. So maybe the rational numbers are actually smaller than the integers. Do you think that could be true?
It doesn't
Possible.
seem like it's true.
Okay, we should probably try to figure out why it's not true.
Well, the rational numbers include the integers.
Aha! The integers are inside of the rational numbers.
So if the rational numbers are smaller than the integers, that wouldn't make any sense.
Very good. Very good. The integers are inside of the rational numbers. So we know this proof, because it's overcounting, says the integers might be bigger, but since the integers are inside, they have to be the same size.
Yeah.
Okay. Very nice. Very nicely done. Okay, so let's go on to something you found interesting in the book.
Right?